Take a look at the glass of water on your desk. Nothing fancy, just ordinary tap water with a few ice cubes floating on top. You've seen this sight thousands of times, but let me ask you, doesn't it strike you as odd? Probably not. Ice floats. End of story. But here's the twist. By the laws of physics, ice shouldn't float at all. Most solids sink in their own liquids. Steel sinks in molten steel. Solid wax sinks in melted wax. Yet water? It shrugs and says, I don't do that. This tiny act of rebellion is one of the strangest physical quirks in nature. Ice is literally lighter than the liquid it comes from. That's not just trivia, it's a cosmic loophole. Without it, winters on Earth would have looked like scenes from a nightmare. Imagine lakes where ice doesn't cap the surface but instead sinks, dragging colder layers down with it. Winter after winter, water bodies would freeze from the bottom up, suffocating fish and locking entire ecosystems under eternal ice. Spring would never fully come back. If ice didn't float, we might not be sitting here at all. And yet, we take it for granted. We clink glasses, chew the cubes, and never stop to think that life itself depends on this glitch. It's as if nature cheated on an exam, and that little cheat code is the reason evolution had a playing field. Scientists call this the density anomaly of water. Normally, when a liquid cools, molecules slow down, pack closer, and become denser. Solid sinks. But water, in its stubborn eccentricity, is different. As it cools toward 4 degrees, it reaches peak density. Go colder, and suddenly it loosens up again, spreading out into a lattice with open spaces, what we call ice. It expands at the exact moment it should contract. Counterintuitive, infuriating, and miraculous. That's why your ice floats. It's not just cocktail aesthetics. It's the reason fish survive winters. The reason rivers thaw in spring. The reason life thrived in places that should have been silent and frozen. Ice forms a floating blanket, an insulating lid, keeping the water below at a survivable temperature. It's not just frozen water. It's frozen mercy. This is the first sign that water is not the obedient, boring liquid you thought it was. It's an outlaw, bending rules in ways that make the world habitable. And density inversion. That's just the opening act. Because once you tug on this thread, you realize water doesn't just bend one rule, it breaks dozens. It's a portfolio of scientific crimes, and scientists are still baffled. Some even whisper that if water behaved like a normal liquid, Earth might never have harbored life at all. That's a bold claim, but not exaggerated. Water's bad behavior is the reason you're alive, sipping it right now. So the next time you look at your glass, don't just see hydration. See a miracle disguised as ordinary. See a lawbreaker in clear costume. And remember, we're only at the beginning of water's list of strange crimes against physics. Alright, let's zoom in. Why is floating ice such a scandal in the world of matter? Because water dares to do what nearly no other substance does. It flips the density script upside down. Think of most materials, cool them down and the molecules slow their jittery dance, snuggle closer together, and the substance gets denser. Solid lead is denser than molten lead. Solid gold. Denser than liquid gold. The pattern is so reliable you could almost call it a law of nature. But then comes water, the anarchist. At around 4 degrees Celsius, liquid water hits its maximum density. Colder than that, instead of becoming more compact, it suddenly puffs up like bread in an oven. When it fully freezes at 0 degrees Celsius, its volume expands by about 9%. The result? Solid ice floats like a rebel buoy. The reason lies in the architecture of water molecules. When temperatures fall, they link arms in a crystalline lattice, held together by those mischievous hydrogen bonds. But instead of stacking neatly and tightly, the molecules lock into an arrangement full of empty space, tiny pockets of nothingness that make ice less dense than liquid water. That empty space is why ice cubes bob in your soda and why glaciers float on the sea. From a purely physical perspective, this is outrageous. Imagine if steel cooled into a version of itself that was lighter and floated on molten steel. We'd rewrite metallurgy textbooks, but with water we shrug. Oh yeah, Ice floats. Cute. Cute? No, existential. That little buoyancy trick is one of the linchpins of life on Earth. Because when ice floats, it doesn't just hover, it shields. A frozen lake's surface becomes a lid, a frosty roof that insulates the living water below. Beneath the ice, fish, plants, and microscopic critters survive, their ecosystem humming along despite the frozen world above. Ice becomes both prison and protector, locking the cold out, keeping warmth in. That insulation is why northern lakes can host life year after year, instead of becoming permanent graveyards. And it's not just lakes. Oceans too benefit from this quirk. Polar seas maintain liquid pockets under their frozen skins, and those become havens for strange resilient life forms. If ice sank, those habitats would vanish. The ocean would turn into a giant freezer from the bottom up. Earth, instead of being the blue planet, might have been the white tomb. Some researchers even speculate that this anomaly of water may have been a decisive factor in Earth's evolutionary path. Without floating ice, climate swings would have been so brutal that complex ecosystems might never have stabilized. Forget mammoths and humans. We'd be looking at a planet of microbes at best, clinging to survival in a global ice desert. So yes, floating ice isn't just a neat parlor trick. It's a cosmic loophole, a cheat code built into physics, one that allowed Earth to keep its lakes liquid, its oceans alive, and its climate relatively stable. All because water molecules insist on forming an airy, lightweight lattice instead of the heavy, compact structure nature expected. And here's the kicker. This is just one of water's dozens of scandals. Ice floating is famous, sure, but water's rap sheet includes boiling at the wrong temperature, hoarding heat like a miser, and pulling off feats of evaporation that put air conditioners to shame. If water were a student in a physics class, it would have been expelled for cheating decades ago. But instead of punishment, life crowned it king. Let's play the what-if game. Imagine a world where ice doesn't float but sinks. At first glance you might shrug, so what? But this tiny twist would turn Earth into a frozen graveyard. Picture a northern lake in December. The surface chills, forms ice, and instead of bobbing like a lid, those crystals plunge downward. More water freezes at the surface, sinks again, and the process repeats like an endless assembly line of doom. Before long, the entire lake is a solid block of ice from top to bottom. Fish, plants, and microbes. Gone. Spring arrives, but nothing thaws. The sun warms the top layer sure, but underneath, a dead, frozen monolith. Now zoom out. Oceans follow the same logic. Year after year, ice accumulates at the seafloor. Within centuries, the deep would be locked into a permanent freezer. Earth would have worn the mask of a snowball planet, perhaps forever. Life might have never climbed out of its microbial cradle. And here's the terrifying part. This isn't science fiction. It's simple physics. What should have happened if water behaved like almost every other liquid? Instead, we lucked out. Ice floats. By staying at the surface, it insulates the liquid beneath, keeping ecosystems alive through winter. Fish still swim, amphibians still hibernate in the mud, bacteria still churn out nutrients, all because ice chose to rise instead of sink. Think about that the next time you skate across a frozen pond. That mirror of ice beneath your feet is both barrier and blessing. It separates you from the life struggling below while simultaneously protecting it. A frozen paradox, hostile to us, merciful to them. It's no exaggeration to say this property of water is one of the cornerstones of life on Earth. It's the reason temperate zones exist, why seasons turn without wiping the slate clean, why ecosystems persist year after year. Without this anomaly, there might not have been forests or civilizations or us. So when you hold a glass of water with floating ice cubes, you're staring at a survival mechanism written into the chemistry of H2O, a reminder that life isn't inevitable. It's balanced on the edge of bizarre exceptions, and this was just anomaly number 1. Water, it turns out, has a whole resume of weirdness. And next on the list is a twist even stranger. Inside this ordinary liquid might be hiding two different kinds of liquid, coexisting like oil and vinegar in a cosmic salad dressing. Here's where water gets even weirder. Scientists suspect that what we casually call liquid water may actually come in two different versions. Not hot versus cold, not pure versus salty, but structurally distinct liquids coexisting in the same glass. Like a secret double life hidden from the naked eye. In the lab, when water is pushed into extreme conditions, supercooled to temperatures well below freezing, or squeezed under intense pressures, it starts to misbehave in ways that standard physics textbooks can't quite explain. Computer simulations suggest that under those conditions, water may split into two forms: low-density liquid, LDL, molecules spread out, linked in a loose, open, tetrahedral network, almost like scaffolding made of sticks. High-density liquid, HDL, molecules jammed together more tightly, cramming in neighbours like passengers on an overcrowded bus. The analogy scientists love is salad dressing. Shake a bottle and oil and vinegar swirl together, one light, one heavy. Now imagine water doing something similar. The same H2O molecules, but organising into two distinct liquid personalities, depending on temperature and pressure. If that's true, it might explain the classic Fordenbild-SCC anomaly, the point where water hits maximum density before expanding again. Think of it as water momentarily torn between its two personalities, part of it trying to stay in high-density mode, part of it sliding toward low-density mode. The tug-of-war could be the reason lakes don't freeze solid and why ice floats in the first place. This idea isn't just theoretical musing. Computer models already show the separation. Experiments with supercooled water droplets hint at similar patterns. Some researchers even suspect that deep inside ice, little patches of low-density and high-density arrangements coexist, like ghostly fingerprints of this duality. And here's the kicker. If confirmed, it means water isn't one liquid, but two liquids wearing the same mask. It would make water not only anomalous, but downright schizophrenic by molecular standards. No other common liquid is known to behave like this. Why does it matter? Because it hints that water's weirdness isn't a random accident. The same double life could be what stabilizes ice's open structure, what gives water its bizarre density curve, and what makes it the life-supporting medium we know. So next time you pour a glass of water, remember, you might not just be drinking one liquid. You might be sipping two at once, blended together in a molecular masquerade. And if that isn't strange enough, wait until we get to the next crime in water's rap sheet. Boiling at the wrong temperature, as if water had bribed the periodic table to let it stay liquid against all odds. Here's the part where water flips the bird at chemistry's family rules. Every liquid has a kind of exit strategy. The temperature at which it boils abandons liquid life and floats off as gas. And if you line up water with its chemical cousins, it should be gone long before your tea kettle even warms up. Look at the periodic table. Water belongs to a family of compounds where a central atom from group 16, oxygen, sulfur, selenium, bonds with hydrogen. That gives us things like hydrogen sulfide, H2S, or hydrogen selenide, H2SE. What do? They boil at temperatures so low you wouldn't even notice them as liquids. H2S, for example, boils at 60 degrees. It never makes it to liquid at room temperature. It's a stinking gas. By that logic, our little H2O, with its tiny molecular weight, should also boil somewhere around 80 degrees, which means at everyday Earth temperatures, water should not be a puddle. It should be vapour, mist, fog, nothing for oceans, rivers, or a refreshing glass. And yet, water holds out. It doesn't vaporize at a chilly 80 degrees. It clings to liquid life all the way up to 100 degrees, a full 180 degrees hotter than chemistry allows. That's not just odd, it's unheard of. It's like watching the skinniest kid in the class outlift all the heavyweights. Why? Again, hydrogen bonds. These little molecular handshakes are stronger than the flimsy Van der Waals forces holding other liquids together. They're so stubborn that water molecules refuse to drift apart until they've been shaken with a serious amount of heat. That's why you can simmer soup, brew tea or sweat on a hot day. without your own body evaporating into thin air. Think about the planetary stakes here. If water boiled at just Earth would never have had oceans. Every droplet would have boiled off into the sky, leaving behind a barren rock with a thin, ghostly veil of vapour. No seas for life to crawl out of, no rivers carving valleys, no waves pounding coastlines into history. Earth would have looked more like Venus, dry, suffocated, and frankly, boring. Instead, water's boiling point rebellion is the reason Earth has vast, stable oceans. And those oceans, they're not just scenery. They're time machines, incubators, and climate regulators. They gave evolution its playground. Without them, the only life Earth might have supported would be the kind scribbled in a chemist's notebook. Molecules too lonely to ever organise into cells. So when you put the kettle on for coffee, you're performing a miracle test. You're watching a liquid defy the rules written for it by physics, clinging to existence in a state where it doesn't belong. Water should be vapour, but it isn't, and thank the universe for that. Because this stubborn streak, this refusal to follow the rules, didn't just save Earth's oceans, it saved Earth itself. Now here's another gem in water's resume of mischief. Not only does it boil at the wrong temperature, it also stretches its liquid range wider than almost anything else its size. Most small molecules, the ones with light weights like water, flip between ice and vapour so quickly you barely catch them hanging around in liquid form. But water, it luxuriates in a liquid state from 2 degrees all the way to 100 degrees at standard pressure. That's a full 100-degree window of liquid comfort, a penthouse suite in the Hotel of Chemistry. Think about how weird that is. If water had followed the example of its cousin, hydrogen sulfide, it would only exist as liquid for a sliver of temperature. Blink and you'd miss it. Imagine trying to build life in that narrow window. Good luck. Molecules would either be frozen stiff or floating away as gas. Stability? Forget it. Evolution? Impossible. But with water, Earth scored the jackpot. That 0-100 Ros's sea range created a giant playground for chemistry. It allowed rivers to flow, lakes to churn with nutrients, oceans to stabilize climates, and eventually it gave life the time it needed to stumble, crawl, and flourish. It's no coincidence that wherever liquid water exists, life seems to flirt with the possibility of showing up. It's as if liquid water sends out invitations. Come on in, the chemistry's fine. And here's the subtle point. It's not just about convenience, it's about resilience. With such a wide range, water can buffer against environmental chaos. A planet can swing hotter or colder without instantly losing its oceans. Earth could weather ice ages and heat spikes, and yet its seas remained. Shifting, yes, but not disappearing. That gave life continuity. That gave ecosystems memory. Compare that to Mars or Venus. Mars is so cold and thin-aired that water evaporates almost instantly. Venus is so blisteringly hot that any past oceans boiled away long ago. Neither had water's stability, and neither kept life as we know it. Earth alone had this golden ticket, a liquid window wide enough to host 4 billion years of evolutionary drama. So, when you dip your hand into a river or listen to the ocean at night, remember, this isn't just wet stuff. It's the rarest state for a molecule like H2O, and the fact that water holds onto this state so stubbornly is why fish swim, forests grow, and we sit here asking questions about it. And yet, this isn't even water's final trick, because not only does it stay liquid where it shouldn't, it also moonlights as Earth's greatest heat manager. Oceans and puddles, sweat on your brow, even that hot bath after a long day, they all work because water is a thermal miser. It stores and hoards heat like no other, smoothing Earth's chaos into something survivable. To really appreciate how spoiled we are with Earth's oceans, let's take a short trip next door, to Venus and Mars. Both planets once flirted with water, but unlike Earth, they couldn't hold on to it. Why? Because water's rebellious boiling point wasn't enough to save them from their own environments. Let's start with Venus. Today, it's a hellscape, blistering at 460 degrees, with an atmosphere thick enough to crush a submarine, If you dropped a glass of water there, it wouldn't even bother boiling. It would flash into vapor and then be torn apart by the savage heat. Billions of years ago, Venus might have had oceans, but the planet lost its delicate balance. The heat rose, the seas evaporated, and the atmosphere turned into a greenhouse runaway train. The irony? Venus is almost Earth's twin in size and composition, yet the lack of stable water doomed it to become the solar system's cautionary tale. Now swing over to Mars, the smaller neighbour. Today it's cold and bone-dry, with rusty deserts and polar ice caps. But Mars too carries scars of a watery past. Ancient riverbeds snake across its surface, and there are deltas where water once pooled. The problem? Mars has a flimsy atmosphere. At such low pressure, liquid water simply can't stick around. It either freezes or boils away instantly. Mars is like a fridge with the door permanently open, too leaky to keep the good stuff inside. Compare that to Earth. Here, liquid water hangs on across an absurdly wide temperature range, thanks to its boiling point rebellion and its knack for stretching that liquid window from 0 to 100 degrees. That stability, combined with Earth's right distance from the Sun and protective atmosphere, gave us not just puddles, but oceans. Oceans that stayed oceans for billions of years. This is why astrobiologists are obsessed with water. Every time a probe lands on Mars or a telescope stares at a distant planet, the first question isn't, is there oxygen or is there soil? It's, is there water and can it stay liquid? Because if the answer is yes, the chances of life go from laughably small to at least possible. Earth, by sheer good fortune, managed to thread the needle. Venus cooked, Mars froze, but our planet kept its seas steady. Not because water is normal, but precisely because it isn't. Its strange physics gave us stability where chaos should have reigned. And that stability brings us to water's next great quirk, its obsession with heat. See, water doesn't just sit quietly in your glass. It hoards energy, tames temperature swings, and single-handedly stops Earth from becoming a place of burning days and freezing nights. If water had a resume, right below makes ice float and boils at the wrong temperature, you'd find another brag. Professional heat hoarder. This is water's specific heat capacity, the amount of energy it takes to raise its temperature by just 1 degree. And spoiler, water's appetite for heat is massive. You've seen this in action without even knowing it. Try boiling a pot of water. You crank the stove, and 5 minutes later, the oil in a frying pan is sizzling like a flamethrower. But the water, still stubbornly lukewarm, as if it's negotiating with the fire. That's because every gram of water demands an absurd amount of energy before it budges even 1 degree. It's like heating up a crowd at a party where nobody dances until they've each been bribed individually. Now, zoom out to Earth. 70% of the planet's surface is covered in water. That means the oceans are essentially a giant thermal battery, sucking up heat during the day, releasing it slowly at night, and levelling out the wild mood swings of our planet's climate. Without this sponge effect, Earth would swing between brutal extremes, frying during the day, freezing at night. Think Mercury, scorching hot sunlight followed by icebox darkness, a place where life, if it even existed, would be constantly whiplashed by temperature chaos. Instead, oceans hoard heat, then drip feed it back into the atmosphere. This is why coastal cities have mild climates compared to inland deserts. Why Britain isn't buried in Siberian snow despite being on the same latitude. Why the Gulf Stream, a river of warm water in the Atlantic, can practically heat Europe like a massive undersea radiator. And the heat hoarding doesn't just save humans, it saves the planet's memory. Since the 1970s, when greenhouse gases began cranking up the global thermostat, the vast majority of that extra heat didn't stay in the air, it sank into the oceans. Without that buffer, the world's climate would already be a violent seesaw. The ocean is buying us time, though how much time is still up for debate. But the story gets even juicier, because water doesn't just hoard heat. When it changes state, say, from liquid to vapour, it pulls off an even bigger trick. It stills energy in bulk, vanishes into the air, and then, miles away, dumps that energy back out. Water, in other words, doesn't just store heat, it moves it. That's the magic of evaporation. And it's why water isn't just Earth's heat sponge, it's also Earth's air conditioner. If you've ever broken into a sweat on a summer day, you've already been saved by one of water's most underrated tricks: its ability to rob heat when it evaporates. This is water's latent heat of vaporization, a fancy term for the absurd amount of energy water demands to make the jump from liquid to vapor. And in practice, it's like having the planet's most efficient air conditioner running non-stop. Here's how it works on you. One bead of sweat evaporating off your skin takes with it about 2,160 joules of energy per gram. That's enough to chill your body without you even noticing. Other liquids? They barely do this. Alcohol evaporates fast, sure, but it doesn't carry away nearly as much heat. Water, in its eccentric generosity, gulps down energy and then vanishes, leaving you cooler than before. It's the ultimate disappearing act, powered by physics. But what works for a human body works even bigger for the planet. When the ocean's surface warms under the sun, trillions of molecules leap skyward, stealing heat with them. That energy doesn't vanish. It hitches a ride inside the vapor, travels with the winds, and eventually crashes down elsewhere as rain. When raindrops form, the stolen heat is released back into the atmosphere. The result? Gigantic weather systems. Hurricanes, thunderstorms, even the monsoon cycle are all fueled by water's knack for packing and transporting heat like a courier service for the climate. It's hard to overstate how critical this is. Without evaporation, the tropics would cook themselves into lifeless ovens, while the poles would stay in eternal darkness and cold. Instead, Earth has a circulation system. Oceans evaporate, clouds carry heat across continents, and rain redistributes it. Water doesn't just cool your forehead, it balances the entire climate engine. This also explains why deserts are unbearable. With little water around, there's no evaporation to steal heat. The sun's energy just sits there, baking the ground until it feels like an oven tray. Contrast that with a humid rainforest. Same sun, but the constant evaporation acts like a planetary misting fan. Sticky? Yes, but survivable. So the next time you curse humidity, remember that clammy sweat and thick air are part of the machinery keeping Earth's thermostat in check. Water is absorbing heat in silence, then moving it across the globe, turning chaos into circulation. But water's eccentric resume doesn't stop here. Beyond floating ice, rebellious boiling points, and its talent for climate control, water flexes another outrageous property. Surface tension so strong it lets bugs walk on water and trees drink skyward. It's like giving an invisible skin to every puddle, every droplet, every ocean wave. And that's our next scandal. Take a glass of water, fill it to the brim, go a little further, add that last drop where you're sure it's going to spill, and yet it doesn't. Instead, the surface bulges up like a rounded dome, stubbornly clinging to itself. That little trick, that surface tension, water's invisible skin. Now, most liquids have surface tension, but water's a show-off. Its molecules grip each other with such fierce cohesion that the surface acts almost like a stretched sheet of elastic. This is why water droplets form perfect spheres, and why, in a sense, each raindrop is nature's attempt at geometry homework. It's also why insects like the water strider can literally skate on ponds. To them, a lake surface is not liquid but trampoline. Each leg dimples the water but never breaks through, as if the insect were wearing divine snowshoes. For humans, it looks like a miracle. For water, it's just Tuesday. But surface tension isn't just for party tricks. It powers one of Earth's most vital processes, capillary action. This is how plants drink. Roots pull in water, and thanks to surface tension plus adhesion, the tendency of water to stick to other surfaces, the liquid creeps upward through impossibly thin tubes. It defies gravity, inching toward the leaves. That's how redwoods get water to their crowns 100 meters up. It's plumbing powered not by pumps but by physics. Imagine the alternative. No surface tension, no capillary rise, no tree taller than a bush. Forests wouldn't exist. Ecosystems would collapse. And you wouldn't be breathing oxygen right now. Every deep breath you take owes itself to the invisible tug-of-war of water molecules climbing leaf by leaf into the sky. And water's sticky skin paradox goes further. That same adhesion is why you can lick your finger to turn a page, but its slipperiness is why a wet floor is nature's lawsuit waiting to happen. Water is clingy and elusive at the same time, a lover and a prankster rolled into one molecule. In short, water doesn't just sit in rivers and oceans. It engineers global architecture, builds forests, fuels oxygen cycles, and lets bugs moonwalk on lakes. Its skin is strong enough to hold life itself, and yet, behind this skin of steel, lies an even deeper superpower. Water isn't just cohesive, it's hungry. Hungry enough to dissolve more substances than any other liquid in the universe, the so-called universal solvent. And that appetite? It's the reason your blood flows, your cells eat, and your body doesn't grind to a halt. Water is full of contradictions. One moment it clings to everything in sight like the world's stickiest glue. The next, it turns a floor into the deadliest skating rink you'll ever walk on. How can one liquid be both Velcro and banana peel at the same time? Let's start with the sticky side. If you've ever wet your finger to turn a page, you've cashed in on water's adhesive nature. Those little H2O molecules love grabbing onto other surfaces, paper, glass, even skin. That's why raindrops cling to windows like tiny transparent barnacles, or why your hands feel tacky after rinsing them, even without soap. Adhesion makes water a natural glue, but take that same glass of water and spill it on the kitchen floor. Suddenly you're auditioning for the Winter Olympics. Why? Because water is also a world-class lubricant. When it spreads out in a thin film, it acts like a microscopic layer of ball bearings, reducing friction to almost nothing. Tires skid, shoes slip, bones break. A single puddle can humble even the proudest human. It sounds contradictory, clingy and slippery, but both come from the same molecular mischief. Those hydrogen bonds, always reaching out, sometimes stick water to surfaces, and sometimes let molecules slide over each other with shocking ease. The result? A liquid that can be both glue and grease, depending on the context. Nature exploits this duality brilliantly. Inside your body, water makes joints flexible, the synovial fluid in your knees and elbows, mostly water acting as a shock absorber and lubricant. On the other hand, water's adhesiveness is why your saliva helps you swallow food, binding crumbs into something smoother. Water's paradox is literally what keeps you standing, moving, and eating. And this strange double life isn't just about convenience, it's another reason why life works at all. Imagine a world where water was only sticky. You'd be walking on goo and cells would be glued shut. Or a world where it was only slippery. You couldn't hold anything together, from tissues to tendons. But with both properties in balance, water threads the needle perfectly. So when you curse after slipping on a wet floor, remember, that same slipperiness is saving your knees, oiling your joints, and keeping you mobile. Water isn't out to get you, it's just multitasking. But this multitasking comes with yet another gift. Water's unmatched hunger to dissolve. Sticky, slippery, and now insatiable. It's the universal solvent, and without that, biology wouldn't just be harder, it would be impossible. Now we get to water's most famous superpower, its appetite. Chemists call it the universal solvent. Of course, it can't dissolve everything, you can still stir your coffee with a spoon. But compared to every other liquid we know, water dissolves more substances, more completely, and more effectively. And that, frankly, is the reason you and I are alive. Why does it happen? It comes down to water's molecular shape. Each H2O molecule is like a tiny V-shaped magnet, with a slight positive charge near the hydrogen ends and a negative charge near the oxygen. When water meets an ionic compound like salt, it swarms the ions. Oxygen atoms with their negative charge grab the positive sodium ions. Hydrogens with their positive charge cuddle up to the negative chloride ions. Surrounded on all sides, the ions lose their grip on each other and drift apart into solution. Salt disappears, but not really. It's just been dismantled and hidden inside water's embrace. This is chemistry's version of a superpower hug. And it's not limited to table salt. Water dissolves sugars, minerals, gases, even nutrients inside your bloodstream. Without this ability, your cells couldn't import what they need or export what they don't. Proteins wouldn't fold, DNA wouldn't replicate, metabolism would sputter. Life is basically water hosting the greatest chemical networking party of all time. Nature relies on it everywhere. Rivers carve valleys by dissolving minerals out of stone. Rainwater leaches nutrients into soil for plants. Inside your stomach, digestion is powered by water breaking down food into molecules small enough to travel into your blood. Even your brain runs on neurotransmitters ferried across watery highways. Without water's dissolving obsession, Earth would just be rocks and dust. No forests, no oceans, no humanity. But here's the irony. For all its fame, the universal solvent label is a little bit of a stretch. Water won't dissolve oils or fats easily. They repel it, like cliques at a bad party. That repulsion is actually what gave rise to cell membranes, oily layers that water can't breach easily, creating little pockets of order where life could start cooking. In a strange twist, water's one weakness, its inability to dissolve fats, is what allowed cells to exist in the first place. So, yes, water is a solvent like no other. It carries minerals from mountains to seas, glucose to your cells, and whispers to the machinery of DNA. It is the bloodstream of the planet, and the bloodstream of life itself. And yet, this is still not the full story. Because once scientists started tallying up all of water's anomalies, they realized the list didn't stop at floating ice, stubborn boiling points, or even its solvent powers. It kept going. 70 separate abnormalities, and counting. By now you might think, okay, ice floats, water holds heat, it dissolves stuff. Fine, it's special. But scientists aren't content with 3 or 4 quirks. When they really sat down and catalogued water's oddities, the list ballooned to at least 70. 70. Imagine being so strange that textbooks can barely keep track of all the ways you misbehave. Here's a taste of that laundry list. Water has an unusually high heat capacity. We covered that. It also has a bizarrely high surface tension, higher than almost any liquid its size. It expands when it freezes instead of shrinking. Its compressibility changes in ways that make no sense. It has an anomalously high dielectric constant, meaning it can separate electric charges better than anything else. Even its sound velocity, the speed at which vibrations travel through it, behaves oddly as pressure changes. It gets weirder. Water is one of the only liquids that can remain supercooled, staying liquid below its freezing point under the right conditions. At extreme pressures, it can form not just one, but more than a dozen types of ice, each with its own crystal structure. Some are denser than liquid water, some are lighter. It's like water has multiple alter egos, each waiting for a chance to appear under just the right conditions. To a casual drinker, this doesn't matter. To a physicist, it's a migraine in liquid form. If water behaved like a normal liquid, its properties would plot neatly on a graph. Density rising smoothly as temperature drops. Boiling point predictable from molecular weight. Instead, water zigzags and swerves like a drunk driver. Every time scientists think they've pinned it down, it throws another curveball. One researcher famously remarked, "If water were discovered today, it would be hailed as the strangest liquid on Earth." Instead, it's so common we forget how bizarre it is. We wash dishes with it. We flush toilets with it. We walk past it every day, blind to the fact that it's breaking more rules than any other substance we know. So what ties all these 70 anomalies together? There is a unifying principle, and it's not just random bad behavior. The culprit is hidden in the molecule's very architecture, in that simple V shape of hydrogen and oxygen, and the invisible glue it creates, hydrogen bonds. Those bonds are the secret string pullers behind almost every one of water's contradictions. Ice floating, high boiling point, universal solvent, sticky slippery paradox. All of it traces back to the same tiny force. Hydrogen bonds are weak enough to break, strong enough to matter, and just quirky enough to turn water into nature's ultimate trickster. So if we really want to crack the case, we have to go microscopic. To stop staring at the glass and start staring at the molecules dancing inside it. That's where the real scandal begins. On paper, water looks boring. H2O, 2 hydrogens, 1 oxygen. End of story. But if it were really that simple, we wouldn't be here talking about 70 scientific headaches. The weirdness begins with geometry. Water isn't a straight molecule, it's bent, shaped like a V, and that little kink is the lever that pries open all its strangeness. Here's why. Oxygen is greedy. It hogs electrons, dragging them closer, while the hydrogens are left electron poor. The result is a molecule with a split personality, slightly negative at the oxygen tip, slightly positive at the hydrogen ends. Think of it as a molecular magnet. One side says plus, the other minus. This polarity is what lets water molecules stick to each other, and to almost everything else. Now, multiply that by trillions. Each water molecule with its little V-shaped magnet is tugging and clinging to its neighbours. Left unchecked, you'd think this should lock water into a rigid solid at room temperature. But here's the twist. The bonds they form aren't permanent. They're hydrogen bonds, stronger than the weak attractions in most liquids, but far weaker than the covalent bonds holding atoms together. They're like handshakes, firm enough to matter, but fleeting, breaking and reforming in trillionths of a second. This is the hidden scaffolding behind water's entire resume of rebellion. Ice floats because hydrogen bonds force molecules into a spacious open lattice. Water boils at a ridiculous 100 degrees because those bonds make molecules cling longer than they should. Water hoards heat because energy gets spent breaking bonds before temperature rises. Even the universal solvent trick? That's water's polarity at work, letting those little V-shaped magnets surround and dismantle other molecules. It's astonishing to think that everything we've covered so far, floating ice, oceans stable for billions of years, life's very chemistry, comes back to this humble V-shape. A geometric accident that turns 3 simple atoms into the most important substance on Earth. And yet, calling hydrogen bonds handshakes is almost too gentle. In liquid water, they weave into a restless shifting network, a crowd where everyone's shaking hands, breaking off, and grabbing someone new every picosecond. It's chaos. Beautiful, ordered chaos. If you want to understand why water is the strangest liquid in the universe, you have to follow those handshakes. You have to watch how molecules cling, part and cling again, all while keeping the liquid flexible and alive. That's what we'll do next. Zoom in on this invisible scaffolding and see how it makes ice feather light and liquid water so stubbornly resilient. So here we are, staring at the true puppet strings of water's strangeness. Hydrogen bonds. They're the reason water doesn't behave like a normal liquid. They're the invisible scaffolding that makes H2O less of a simple liquid and more of a living architecture. Picture it. Each water molecule has 2 tiny hydrogen hands and 2 oxygen hooks. With this setup, every single molecule can link to 4 neighbours at once. That's unusual. Most liquids don't have the chemistry to form such a social network. But water is the extrovert of the molecular world. It grabs everyone in sight, holding them in a sprawling 3-dimensional handshake. Now, hydrogen bonds are quirky. They're stronger than the flimsy attractions in, say, liquid nitrogen, but weaker than the hard-wired covalent bonds that hold atoms together. This middle ground is what makes them magical. They're strong enough to matter, but weak enough to break easily, and break they do trillions of times every second. Water's entire network is constantly rearranging, molecules pairing up, breaking apart, then linking with someone new. It's like an eternal square dance, except nobody ever stops moving. This constant shifting is why water is both structured and flexible. In ice, those hydrogen bonds lock molecules into a neat, open lattice, leaving gaps that make ice less dense than liquid water. That's why ice floats. In liquid water, the bonds are restless, forming, breaking, reforming, so the molecules pack closer together, giving water its dense, fluid character. And the rebellion doesn't stop there. Those bonds are also why water's boiling point is ridiculously high, for such a lightweight molecule. Normally, heat would easily scatter the molecules of something this small. But because hydrogen bonds cling so tightly, you have to pump in an absurd amount of energy to break them all and turn water into vapour. That's why oceans can simmer under a blazing sun without instantly vanishing into steam. Even water's famous heat hoarding? Chalk it up to hydrogen bonds again. Before water's temperature can rise, energy first has to break apart these little molecular handshakes. It's like trying to heat a party where everyone keeps stopping to greet each other. You spend most of your energy just on the introductions. So when scientists talk about water's anomalies, they're really talking about one thing: the fallout from hydrogen bonds. Floating ice, high boiling point, heat sponge, universal solvent. Every one of these quirks ties back to this invisible network of bonds, forever linking and unlinking, forever rewriting the structure of the liquid beneath your glass. It's humbling, really. The survival of ecosystems, the stability of our climate, even the chemistry of life. All of it hinges on weak, flickering bonds between tiny molecules, fragile enough to snap in a heartbeat, yet powerful enough to hold up an entire planet. But what happens when those bonds settle down completely, freezing into rigid order? That's when ice reveals its own strange character, a solid that's somehow lighter than its own liquid. Let's take the same characters, our chatty little H2O molecules, and put them on two different dance floors. In liquid water, they're in a frantic square dance, partners swapping every trillionth of a second, hands clasping and breaking, the whole floor buzzing with chaos. But in ice, suddenly the music slows and the dancers lock into formation. No improvising, no swapping partners, just a strict crystalline waltz. In this frozen choreography, hydrogen bonds snap into a rigid lattice. The oxygen atoms spread apart just far enough to keep everyone evenly spaced, and the hydrogens act like the connecting rods of scaffolding. The result is a surprisingly open structure, full of empty pockets. Think of it as a molecular honeycomb, beautifully ordered but riddled with space. And that empty space is the secret behind one of water's strangest tricks, ice being lighter than liquid water. Most solids are denser than their liquids. When you freeze molten iron, for example, the atoms pack tighter and the solid sinks. But ice goes the other way. By locking itself into a honeycomb, it actually takes up more room than the liquid it came from. That's why your frozen water bottle bulges or bursts. The liquid expands as it freezes, ignoring every other liquid's etiquette. This difference in choreography explains why ice floats. Its airy structure makes it less dense than the restless jumble of liquid water beneath. And this single property, as we've seen, is why lakes and oceans don't turn into frozen tombs every winter. It's also why frost heaves tear up roads, why frozen pipes burst in the winter, and why glaciers floating on seas can drift for thousands of miles. Ice is both fragile crystal and unstoppable bulldozer. But here's what makes it magical. Both phases, solid and liquid, are playing with the same basic tools. Same H2O molecules, same hydrogen bonds. The difference is choreography. In liquid form, the bonds are loose, temporary, dancing partners coming and going. In solid form, the bonds lock into a permanent embrace, freezing space into the structure. It's almost poetic. The very same bond that lets water flow so flexibly is also the one that creates the rigid, airy beauty of ice. One moment it's chaos, the next it's symmetry. And out of that symmetry comes buoyancy, insulation, and the preservation of life through brutal winters. But here's the kicker. Just because those bonds look stable in ice doesn't mean they're quiet in liquid. In fact, the real drama is in the liquid phase, where hydrogen bonds break and reform faster than you can blink. To understand water's flexibility and why it balances between order and chaos so perfectly, we have to zoom in on this molecular speed dating. Let's zoom into a single drop of liquid water. To the naked eye, it looks calm, still, almost boring. But at the molecular level, it's absolute pandemonium. Imagine trillions of dancers on a floor, each clasping hands, letting go, then grabbing a new partner, over and over, at a tempo so fast our brains can't even picture it. That's what hydrogen bonds are doing inside every drop. On average, a hydrogen bond in liquid water lasts about 1/trillionth of a second. That's 0.21 seconds. Blink, and billions of bonds have already broken and reformed. It's as if the entire network of water is constantly collapsing and rebuilding itself again and again, without ever losing its overall structure. Like a city where every street is being ripped up and replaced in real time, but somehow traffic never stops. This dynamic network explains why water hits that sweet spot between chaos and stability. If the hydrogen bonds were too strong, water would be stiff and glassy, refusing to flow. If they were too weak, water would behave more like a gas, with molecules flying apart and scattering. Instead, it lands in the Goldilocks zone, bonds strong enough to keep it cohesive, but weak enough to break and reassemble on the fly. That balance is crucial for life. Inside a cell, nutrients, proteins, and DNA rely on water's constant shuffling. Molecules need room to move, but they also need the surrounding fluid to remain organized enough to carry signals, stabilize reactions, and keep the whole system coherent. If water didn't have this dynamic handshake quality, cells would either freeze up like statues or disintegrate into mush. Even at the planetary scale, this property matters. The fluidity of oceans, the way rivers carve valleys, the balance of heat in the atmosphere. None of it would work if water were locked solid at room temperature or flew apart like vapor. The fact that hydrogen bonds are fleeting yet reliable makes Earth's entire climate system possible. Think about that for a moment. Every sip of water, every wave in the ocean, every heartbeat pumping blood, it all depends on bonds that exist only for 1/trillionth of a second. Bonds so brief they're gone before you can even say the word bond. And yet, because they reform instantly, the liquid as a whole never loses its integrity. Its stability born out of chaos. But water's story doesn't stop at frantic handshakes, goes smaller, and the weirdness deepens. Because those little protons in hydrogen, the lightest particles in the atom, don't just sit politely in place. At the quantum level, they start doing something almost unbelievable, tunneling, leaping, and blurring in ways that classical physics can't explain. Just when you thought water couldn't get any stranger, the quantum world crashes the party. Down at the subatomic scale, water's hydrogens, the tiniest, lightest atoms in the universe, refuse to sit still. They don't just vibrate politely in place. No, they pull a quantum stunt called tunneling. Here's the idea. In classical physics, if you're stuck behind a wall, you either climb over it or stay put. Quantum physics laughs at that. Particles so small, like protons, sometimes just appear on the other side as if the wall never mattered. No climbing, no breaking through, just poof. Hello, other side. In water, this means the protons in hydrogen bonds sometimes hop between two oxygen atoms in ways no classical model predicts. They blur, hover, and shift, existing in two places at once like over-caffeinated ghosts. This quantum jitter tweaks the bond strengths, reshapes the network, and ripples outward into water's everyday behavior, its density, its melting point, even the way it carries heat. And we can actually see hints of this. With ultra-fast lasers, scientists have caught snapshots of bonds shrinking and releasing energy in femtoseconds, suggesting quantum fluctuations are at play. It's like watching the molecular scaffolding of water breathe, inhale, exhale, twitch, at a tempo too fast for human imagination. But here's the real kicker. Swap out hydrogen for its heavier cousin, deuterium, and the whole system changes. That's heavy water. Same chemistry, but with slightly heavier protons. Suddenly, the quantum tunneling slows down, freezing points shift, biological systems struggle, feed too much heavy water to an animal, and its metabolism collapses. Just that tiny change in atomic weight is enough to derail life. That's how sensitive biology is to water's quantum weirdness. So let's pause here. Floating ice, wide liquid range, solvent power, all of it already sounds like a miracle, but underneath it all there's a layer of physics so strange it makes scientists squint. Water works not just because of chemistry, but because of quantum effects flickering at subatomic speeds. It's a sobering thought. The glass of water on your table is also a quantum playground. Every sip you take contains protons tunneling, bonds flickering, molecules jittering in ways that defy common sense. Life didn't just depend on water being weird at the human scale, it depended on water being quantum weird at the tiniest scale possible. And we've only been talking about what happens in a drop. Scale it up to oceans, to clouds, to the whole Earth, and water starts writing the script for climate, geology, and even history itself. Let's linger for a moment on this heavy water idea, because it's more than just a quirky trivia fact. It's a reminder of how finely tuned life is to the strange properties of ordinary H2O. Heavy water, chemists call it D2O, is just like normal water, except each hydrogen atom is replaced with deuterium, an isotope of hydrogen that carries an extra neutron. Same chemistry, same basic look, but just a little heavier. You'd think, so what? Water is water, right? But no, that tiny change tips the balance of quantum motion. Deuterium's protons don't tunnel as easily, the bonds rearrange differently, and suddenly water's dance slows down. The consequences are dramatic. Heavy water freezes at a higher temperature than normal water. Ice made from it actually sinks. No cozy floating blanket, no insulation for life. And inside living systems, the difference is even starker. At first, cells tolerate small amounts of heavy water, but as the ratio climbs, metabolism falters, enzymes stumble, and eventually life grinds to a halt. To most organisms, heavy water is toxic. Not because it's chemically poisonous, but because biology is so exquisitely tuned to the quirks of ordinary hydrogen's featherweight jitter. This is wild if you think about it. Swap one subatomic particle, and suddenly water, the substance that makes life possible, becomes hostile. Fish wouldn't swim in it, plants wouldn't grow in it, humans wouldn't survive drinking it. Heavy water is a subtle poison precisely because it isn't different enough. It looks too much like normal water, but it dances to the wrong rhythm, tricking biology into collapsing, and yet heavy water has its uses. Scientists exploit it in nuclear reactors, where its slightly different bonding properties make it an ideal moderator for chain reactions. In medicine, small controlled doses can be used as tracers, marking metabolic pathways without harming the patient. It's one of those rare cases where the wrong version of water has become a powerful tool. But the bigger point is this. Life didn't just happen to use water. Life evolved in partnership with this specific kind of water, H2O, with lightweight protons that tunnel and jitter just enough to give hydrogen bonds their peculiar balance. If Earth's oceans had somehow been made of heavy water, life as we know it might never have appeared. So the next time you drink from a glass, remember, you're sipping a very particular version of water, fine-tuned at the atomic level to be life's perfect medium. Change just one detail, a single neutron in the wrong place, and the whole miracle collapses. But now, let's widen the lens again. We've peered into molecules, bonds, and protons. What happens when scientists use their most powerful tools to watch these bonds in action? The answer: they catch glimpses of a molecular dance so fast, so delicate, it looks like nature's secret choreography. For centuries, water's mysteries were invisible. Scientists could speculate, scribble equations, argue in lecture halls, but nobody could see hydrogen bonds in action. They were too small, too fast, too fleeting. Then came the 21st century with a new kind of camera, ultra-fast lasers capable of firing pulses shorter than a trillionth of a second. Suddenly, the invisible scaffolding of water was caught mid-dance. Here's what those lasers revealed. When water molecules link by hydrogen bonds, they don't just sit there. They stretch and compress like tiny springs, vibrating at speeds our brains can't fathom. In femtoseconds, that's a millionth of a billionth of a second, the bonds snap tight, relax, and snap again, like heartbeat rhythms too quick for the eye. In one experiment, scientists zapped supercooled water with an ultra-fast pulse and watched as the hydrogen bonds shivered, collapsed, and rebuilt themselves in real time. For the first time in history, the molecular square dance wasn't just theory. It was visible, and what they saw was almost poetic. The network wasn't random chaos. It had a kind of fluid choreography. Molecules weren't just bouncing around, they were constantly negotiating, exchanging partners, tightening and loosening in sync. It was like watching an orchestra where every note lasted only an instant. But the music never stopped. This confirmed something profound. Water's strangeness isn't a bug. It's a feature of its restless living network. It's the continual building and breaking of bonds, this ceaseless improvisation that gives water its unique powers, its heat hoarding, its density quirks, its solvent hunger. The magic isn't in static structure, it's in motion. But ultrafast lasers also uncovered something even weirder: quantum ripples. Protons weren't just vibrating, they were tunneling, slipping between oxygen atoms in ways that defy classical logic. In some experiments, the bonds seemed to flicker between states, as if the molecules couldn't decide where they wanted to be. Water, it turned out, is not just chaotic, it's indecisive at the quantum level. And here's the kicker. These ghostly flickers aren't just laboratory curiosities. They ripple upward into the macroscopic world. They're why ice floats, why oceans absorb heat, why your sweat cools your skin. Every climate pattern, every forest, every living cell traces back to these ultra-fast tremors inside a glass of water. So when scientists watch hydrogen bonds twitch under femtosecond lasers, they're not just doing abstract physics, they're watching the machinery that keeps Earth habitable. They're glimpsing the quantum heartbeat of life itself. But let's not stay trapped at the microscopic scale, because water isn't just a local miracle. It's not confined to your glass, your ocean, or even your planet. Out there in the vast dark of space, water shows up everywhere, clinging to comets, hiding in moons, drifting between stars. And that cosmic presence changes the story from water is weird to water is universal. It's tempting to think of water as a parochial thing, our oceans, our rainstorms, the glass in your hand. But step outside Earth for a moment, and the story explodes in scale. Water isn't a local oddity, it's cosmic. Start small, comets. Those icy vagabonds aren't just dirty snowballs, they're time capsules of the early solar system. Many carry water ice older than Earth itself. When they swing close to the sun, they leave behind long tails of vapour, like signatures scribbled in frozen ink. Some scientists even argue comets may have delivered a good chunk of Earth's original water supply. In that sense, the oceans aren't just Earth's, they're hand-me-downs from deep space. But comets are only the beginning. Zoom out to interstellar space, the dark void between stars. Even there, water lurks. Inside cold molecular clouds, telescopes detect vast reservoirs of water vapour and ice grains clinging to dust. These clouds are stellar nurseries, places where new stars and planets are born, which means water isn't just hitching rides, it's woven into the very process of world-making. The scale is staggering. In 2011, astronomers discovered a cloud of water vapour near a quasar 12 billion light-years away. How much water? Enough to fill Earth's oceans 140 trillion times over. And here's the kicker, that water existed when the universe was barely a toddler, just 1.6 billion years after the Big Bang. The message is clear. Water is ancient, abundant, and everywhere. Closer to home, the story repeats. Mercury has water ice hiding in the shadows of craters. Mars has polar caps and maybe underground aquifers. Jupiter's moon, Europa, is practically a water world wrapped in ice. Saturn's moon, Enceladus, sprays salty water into space from geysers at its south pole, misting the cosmos with evidence of a hidden ocean. If Earth is the blue planet, it's only because we happen to live on one where liquid water struts its stuff on the surface. Elsewhere, it lurks in disguise. This ubiquity flips the narrative. Water isn't rare, it's routine. It's not the quirky exception of our world, but a standard ingredient in the universe's recipe book. Hydrogen and oxygen are both abundant, and when they meet, water forms almost inevitably. The real anomaly may not be water itself, but the fact that Earth managed to keep it liquid, balance right in the Goldilocks zone. So the next time you rinse a dish or run a bath, imagine the same molecules drifting in interstellar clouds, freezing on comets, or churning in alien seas. The liquid in your sink is kin to the liquid that shaped moons, carved canyons on Mars, and maybe, just maybe, nurtures life in a hidden ocean light years away. And speaking of alien oceans, let's head there next. To worlds where water isn't just decoration, but the stage on which an entirely different kind of biology might emerge. When we talk about oceans, we usually mean Earth's sprawling blue blankets, the Pacific, the Atlantic, the Indian. Vast, yes, but still tiny puddles compared to what the universe has in store. Because in 2011, astronomers pointed their telescopes at a quasar, a monster black hole feasting in a galaxy 12 billion light-years away, and what they found was jaw-dropping. The largest known reservoir of water in the cosmos. How large? Try this. It holds 140 trillion times the amount of water in all of Earth's oceans combined. That's not a typo. It's a number so absurd it makes our planet's seas look like a raindrop on a windshield. And remember, this wasn't discovered in some quiet corner of the cosmos. It was wrapped around a black hole swirling in a hot, luminous maelstrom of gas. The implications are wild. This water existed when the universe was still young, barely 1.5 billion years after the Big Bang. In other words, water didn't arrive late to the cosmic party. It was there almost from the beginning, woven into the fabric of star formation and galaxy building. And the more we look, the more we find. Across the Milky Way, radio telescopes sniff out water vapor in star-forming regions. Spectrographs spot icy signatures on comets, asteroids, and even exoplanets orbiting distant suns. Water isn't exotic, it's routine. Where hydrogen flows and oxygen burns in stars, water tags along like an inevitable sidekick. This discovery reframes the question of life. It's no longer, is there water out there? The answer is a deafening yes. The question becomes, where is water stable enough to stay liquid? Because liquid water is the stage on which biology performs. Frozen water is inert, vapor water is fleeting, but liquid water is alive with possibility. That's why NASA's mantra has been so simple for decades. Follow the water. Every rover on Mars, every probe sent to icy moons, every telescope peering at distant planets, all of them are, in one way or another, hunting for liquid H2O. And the next stop on that hunt brings us closer to home, to 2 icy moons in our own backyard that may be hiding oceans far bigger than anything on Earth, Europa and Enceladus. If Earth's seas are the cradle of life, these alien oceans might be its second chapter. Let's travel to the outer solar system, where 2 of the most promising candidates for alien oceans lie hidden beneath shells of ice. First stop, Europa, a moon of Jupiter. At first glance it looks dead, just another frozen rock in orbit around a gas giant. But look closer, and you'll see long cracks, streaks and ridges across its surface, like veins under pale skin. Those are signs of movement, evidence that something stirs beneath the ice. Scientists now believe Europa hides a global ocean beneath its frozen crust, an ocean perhaps twice the volume of all Earth's combined. The ice acts like a lid, but tidal forces from Jupiter's immense gravity knead the moon like dough, keeping the ocean liquid. That means Europa may not just have water, it may have it in abundance. Sloshing in the dark, warmed from below, sealed from above. Now shift your gaze to Saturn's moon Enceladus. Smaller than Europa, barely 500 kilometers across, it shouldn't be able to hold much heat. And yet, something astonishing happens at its south pole. Enceladus erupts. Geysers shoot plumes of water vapor hundreds of kilometers into space, glittering like cosmic fountains. Spacecraft flying through those plumes, most famously Cassini, found not only water but salt, organic molecules and tiny grains of silica. In other words, the chemical ingredients of life. If that doesn't give you chills, consider this. Those plumes almost certainly come from a subsurface ocean, one in direct contact with Enceladus's rocky core. Water plus rock playa heat plus chemistry. That's the same cocktail that once brewed life on Earth. And here's the kicker. Both Europa and Enceladus are locked away from sunlight. No cosy photosynthesis here. If life exists in their oceans, it would have to rely on chemical energy, just like the microbial communities living around hydrothermal vents at the bottom of Earth's seas. In other words, alien life might already be thriving in the dark, feeding on the planet's internal chemistry instead of the sun. This is why NASA, ESA, and every space agency worth its salt has their eyes fixed on these moons. Missions like Europa Clipper and the proposed Enceladus Orbolander are designed to sniff, probe, and maybe even taste those waters. Because if we find life in a second ocean, right here in our own solar system, it would prove a staggering point. Life is not a rare accident. Life is what water does when given the chance. But even if Europa and Enceladus are lifeless, their mere existence reshapes our perspective. Earth is no longer the only ocean world. The cosmos is littered with them, hiding under crusts of ice, waiting to be discovered. And that means our own story, the story of life, might just be one chapter in a much larger book. Let's pull our gaze back to two familiar neighbours, planets we've romanticised, studied, and in some ways, mourned. Because both Mars and Venus once had water, maybe even oceans, and both lost it in catastrophic ways. Start with Mars. Today it's a dusty desert, its skies thin and pink, its rivers dry scars across the surface. But billions of years ago, Mars was blue. Orbital images show valleys carved by flowing rivers, deltas where water once pooled, and minerals that only form in lakes. It wasn't just a trickle. Scientists believe ancient Mars had seas, maybe even an ocean in its northern hemisphere. Then, as its magnetic field faded, solar winds stripped its atmosphere. The air thinned, the pressure dropped, and liquid water boiled away. What was left froze underground or at the poles, leaving behind a dry husk that still whispers of its watery past. Venus tells a darker story. If Mars died of thirst, Venus drowned in fire. Evidence suggests Venus may once have had oceans too, calm, shallow seas under a gentler sun. But as greenhouse gases built up in its atmosphere, the planet spiraled into a runaway effect. Oceans evaporated, water vapor trapped more heat, and the cycle fed itself until the surface boiled. Today, Venus is a hellscape, 460 degrees Celsius, hot enough to melt lead, with clouds of sulfuric acid choking the skies. It is, in a sense, a graveyard of water. These twin stories matter because they remind us how fragile the balance is. On Earth, water has persisted in its liquid state for billions of years, thanks to a rare cocktail of factors: distance from the sun, a protective magnetic field, active geology, and of course, water's own bizarre properties. Change any variable, and you get a Mars or a Venus instead of a blue Earth. But here's the strange part. Even in their ruined states, both planets still hold traces of water. Mars has ice caps, frozen glaciers, maybe briny puddles deep underground. Venus has tiny hints of water vapor high in its atmosphere. They're ghosts of the oceans they once held, echoes of what could have been. When scientists say, follow the water, they don't just mean where it is now, they also mean where it used to be. Because even if the seas dried up or boiled away, water leaves fingerprints, and those fingerprints might carry clues about whether life once had its chance on these planets. So while Europa and Enceladus tempt us with the possibility of alien oceans today, Mars and Venus remind us of the other side of the story, how easily oceans can vanish, and how close we ourselves might have come to losing ours. After Mars's thirst and Venus's inferno, Earth feels almost suspiciously lucky. Ours is the blue planet, glowing with oceans so vast they dominate every satellite photo. 70% of Earth's surface is water, and from space, continents look like islands floating in a cosmic sea. But here's the irony. Earth's water is a razor-thin film. If you could gather every drop, oceans, lakes, rivers, groundwater, just glaciers, and roll it into a sphere, it would be only about 400 kilometers across. That's smaller than the United States. On a planet 12,700 kilometers wide, our oceans are just a thin skin. Life is balancing on a watery film spread across a rock. And yet, what a film it is. Those oceans are climate engines, absorbing heat, moving it around the globe in colossal conveyor belts of current. They regulate weather, carry nutrients, and drive the carbon cycle. Without them, Earth's continents would bake by day and freeze by night, swinging between extremes like Mars or the Moon. It's easy to forget how precarious this balance is. Earth sits in a narrow orbital band called the habitable zone, not too close to the Sun, like Venus, not too far, like Mars. Add in our magnetic field, shielding us from solar radiation, and our geologic churn, recycling carbon through volcanoes and tectonic plates, and you get a planet that keeps water liquid across billions of years. And water, in turn, has rewarded us with life. From the first microbial mats in ancient seas to coral reefs and whales, water has been the stage for Earth's grandest experiments. Even land dwellers like us are still tethered to it. Our bodies are 60% water. Our cells are tiny saltwater chambers. Every thought, every heartbeat, every breath passes through water's molecular scaffolding. But here's something we rarely pause to consider. Earth's oceans may not be eternal. They're the product of delicate balances, solar output, atmospheric chemistry, tectonic activity that can shift. One day, in the far future, as the sun brightens, Earth might tip toward Venus's fate. The oceans could evaporate, the sky fill with steam, and our blue world turn pale and dry. For now, though, we're perched in a rare window, a planet drenched in liquid water, balanced between too little and too much, just long enough for life to flourish. Earth is a cosmic sweet spot, and water is the reason it sings. But that leads to a final haunting question. If water is everywhere in the universe, and life on Earth depends on it so deeply, does that mean life itself is common too? Or are we the fluke, the only creatures lucky enough to sip from this fragile universal miracle? Here's where things get truly unsettling. We've established that water isn't rare. It's not Earth's special privilege. It's on comets, on moons, in interstellar clouds, around distant stars. If water is common, and if life needs water, then shouldn't life also be common? That's the question that keeps astrobiologists awake at night. On Earth, life appeared almost as soon as the planet cooled. Within a few 100 million years, microbes were thriving in the oceans. That's a blink of an eye on cosmic timescales, which suggests that, given water, life wastes no time in getting started. But then comes the paradox. If water is everywhere, and life sprouts so easily, where is everybody? Why haven't we seen clear signs of extraterrestrial civilizations? This is the famous Fermi paradox. One answer might be that while water makes life likely, it doesn't guarantee intelligence. Microbes may be abundant across the cosmos, quietly bubbling away in alien oceans, but perhaps they rarely evolve into toolmakers, storytellers, or species building radio telescopes. Still, the fact remains. Wherever we've looked on Earth, boiling vents, acidic lakes, Antarctic ice, life clings on, as long as water is present. Extremophils have taught us that biology doesn't scare easily. If tiny shrimp can thrive in scalding hydrothermal vents and microbes can snack on radiation inside nuclear reactors, then the salty oceans of Europa or the geysers of Enceladus don't sound far-fetched at all. And here's the poetic twist. Some of the water on Earth predates the Sun. Studies of isotopes suggest a fraction of our oceans came from ancient interstellar ice, older than our solar system itself, which means every sip you take may contain molecules forged before Earth even existed. When we drink water, we drink cosmic history. So maybe life really is a cosmic pattern, written in water's peculiar physics and spread across galaxies. Or maybe Earth is the rare planet where the balance held long enough for complexity to bloom. We don't yet know. But every drop of water whispers the same message. Where I flow, possibility follows. And that brings us full circle. Water is not just a background character in Earth's story. It's the main stage, the director, the silent scriptwriter. Without its bizarre quirks, floating ice, sticky cohesion, heat hoarding capacity, we wouldn't be here. Water isn't ordinary, it's the miracle masquerading as mundane. Next, let's tie the story together. From mythology to modern science, water has always been more than chemistry. It has been symbol, ritual and meaning, humanity's attempt to honour the substance that makes us possible. For as long as humans have been telling stories, water has been more than just chemistry. Long before we had lasers to watch hydrogen bonds flicker, we had myths and rituals that treated water as sacred. And in a way, those ancient people weren't wrong. Think about it. Every culture you can name has woven water into its cosmology. In Mesopotamia, creation began with the mingling of fresh and salt waters, the gods Apsu and Tiamat. In Greek myth, Oceanus was the endless river encircling the world. In the Hebrew Bible, God's spirit hovers over the waters before light even exists. In Hindu tradition, the Ganges is not just a river, but a goddess, purifier of sins. Even the Norse imagined their cosmos beginning with ice melting into drops that birthed life. Why such obsession? Because people intuited what science now proves. Water is the boundary between life and death. It cleanses, nourishes, heals. It also drowns, erodes, destroys. No wonder it shows up in baptism, ablution, purification rites. To wash in water is to be reborn. To thirst is to wither. Water is both cradle and coffin. And here's the irony. Even as science has stripped the cosmos of gods and spirits, it has, in some ways, vindicated those ancient intuitions. Water really is miraculous. Not because it's magical, but because its physics are so wildly improbable. Ice floats, heat lingers, bonds dance and break, quantum jitters reshape its structure. None of this had to be true, and yet it is. Which brings us back to us. We've traced water from molecules to moons, from quantum flickers to cosmic oceans, and every step of the way, the story circles back to the same truth. Water is the great connector. It binds protons in subatomic dances. It binds ecosystems in rivers and rain. It binds cultures in myth and ritual. And it binds us as fragile creatures who are, in the end, mostly water ourselves. So maybe those ancient myths weren't just superstition. Maybe they were an instinctive reverence for the one thing that is both utterly ordinary and utterly essential. A recognition that in every glass of water, in every drop of rain, in every tear shed, there is something worth bowing to. And that leaves us with one last reflection. Water is not just a substance. It's the quiet architect of existence. The miracle that hides in plain sight. The closest thing we have to proof that the universe, in all its cold indifference, still allows for life, for beauty, for continuity. If water is the architect of existence, it's also the architect of history. Human civilization has always flowed where the water flowed. Think of the Nile, the Tigris and Euphrates, the Indus, the Yellow River. Every one of them a cradle of civilization. Those rivers weren't just convenient, they were destiny. They dictated where cities rose, where armies marched, where cultures collided. Egypt without the Nile is just desert. Mesopotamia without the Tigris and Euphrates is just dust. Even today, our modern cities hug coasts and rivers, living off that ancient bargain. Water gives life, but only if you settle near it. And water hasn't just fed us, it has divided us. Empires rose on naval power, from Athens to Britain. Whoever commanded the seas commanded the world. Trade routes, wars, colonization, they all flowed with water. Salt water carved history as surely as it carved coastlines. It also inspired some of humanity's strangest quests. Alchemists once dreamed of turning lead into gold, but explorers were obsessed with turning oceans into shortcuts. Columbus, Magellan, Zheng He, all chasing horizons, driven by the idea that water was not barrier but passage. Oceans became both moat and highway, isolation and connection. Even in our own time, water shapes geopolitics. Nations argue over rivers that cross borders, dams that strangle downstream neighbours, glaciers that shrink with climate change. Wars of the future may not be fought over oil, but over water, and in some places they already are. What's striking is how invisible this control can be. You and I turn on a tap and barely think about it. But behind that simple act is a whole infrastructure, a whole political machine. In that sense, water still governs us, quietly, relentlessly, just as it did when pharaohs prayed for the Nile to flood. So when we call water ordinary, it's almost comical. Ordinary things don't move empires, don't spark wars, don't cradle civilizations. Ordinary things don't dictate the rise and fall of history. And yet, here's the twist. Water didn't just shape our story. It shaped Earth itself, long before humans. The valleys, the canyons, the continents, all etched and sculpted by water's patient hand. Next, let's step back from human history and look at how water has been the planet's slow, steady geologist. Before humans built their first cities or carved their first monuments, water was already at work shaping the planet. Patiently, relentlessly, without pause. If Earth is a canvas, water is the brush that painted it. Take the Grand Canyon. It wasn't forged by fire or earthquakes alone. It was sculpted drop by drop, as the Colorado River gnawed through rock for millions of years. Think of that. A trickle of water, persistent enough to slice a continent. Mountains bow before glaciers, valleys deepen under rivers, coastlines retreat before waves. In the quiet arithmetic of geology, water always wins. Rain doesn't just fall, it infiltrates, seeps, and erodes. Over centuries, it hollows caves, dissolves limestone, leaves behind cathedrals of stone adorned with stalactites and stalagmites. Rivers don't just flow, they migrate, meander, abandon old channels and carve new ones, redrawing maps at a pace too slow for the eye but too powerful to ignore. Even deserts bear water's fingerprints. Dry dunes are shaped by ancient rivers that vanished thousands of years ago. Fossilized deltas lie buried beneath the Sahara, proof that where sand now rules, water once reigned. And let's not forget glaciers, rivers of ice that grind mountains to rubble. The fjords of Norway, the Great Lakes of North America, the fertile soils of Europe, all are gifts of ice, sculpted in the last great glaciation. When ice retreats, it leaves behind valleys, lakes, and plains that become the stage for human history. In this sense, water is the planet's most patient geologist. It doesn't shout like a volcano or strike like an earthquake. It whispers, erodes, dissolves, carves, and yet its impact dwarfs them all. Fire may be dramatic, but water is eternal. And here's the poetic irony. The same molecule that builds glaciers and carves canyons also fills teacups and trickles from faucets. The force that shaped the Alps and the Himalayas is the same one that swirls in your glass when you stir a spoon. Scale changes, but the actor remains the same. So when we call water ordinary, we miss the point. Ordinary doesn't sculpt continents. Ordinary doesn't chisel history into stone. Water is a slow-motion artist, and Earth is its gallery. But even that isn't the end of the story, because water isn't just sculptor. It's also memory. It carries the record of climates, of ages, of extinctions, frozen in ice cores and locked in sediments. If you want to read Earth's diary, you don't look at rocks first, you look at water. Here's a strange thought. Water remembers. Not in some mystical way, but in a literal physical sense. Every glacier, every ice sheet, every drop buried in ancient sediments is a time capsule, holding whispers of climates long gone. Take ice cores from Antarctica. Scientists drill kilometers down, pulling up cylinders of frozen history. Each layer is a year, sometimes even a season, of snowfall compacted into ice. Trapped inside are tiny bubbles of air, perfect little samples of Earth's atmosphere from thousands, even hundreds of thousands of years ago. By studying the ratios of gases, we can read temperature swings, volcanic eruptions, even the fingerprints of human industry. It's a climate archive written not in books, but in frozen water. Sediments tell the same tale. Rivers carry minerals, pollen, and organic matter into lakes and seas, where they settle in thin, layered sheets. Drill down, and you can reconstruct droughts, floods, mass extinctions. Water doesn't just shape landscapes, it records them. And it's not just ancient history. Today, glaciers are vanishing, ice sheets are retreating, rivers are shifting course. All signs written in water that our current age will leave a distinct scar in the geological record. Future scientists, if there are any, will read our time in layers of ice and silt, and they will know us not by our monuments, but by the way we disturb the hydrological cycle. There's something humbling about that. Empires rise and fall, but the true chronicler of Earth is water. It saw the dinosaurs drink from its rivers. It carved the valleys where our ancestors first walked. It now carries our pollutants, our plastics, our fingerprints, and it will outlast us, writing the story of humanity in its currents and sediments. Which brings us full circle. Water is not just substance, not just chemistry, not just myth. It's a sculptor, a memory keeper, a cosmic traveller, and the quiet hand behind life itself. And perhaps the greatest miracle is that we still treat it as ordinary, turning on taps, filling bottles, sprinkling it on lawns, as if we weren't dealing with the most extraordinary liquid in the universe. So the next time you take a sip, pause for just a second. Inside that glass may be molecules older than the sun, bonds flickering at quantum speeds, echoes of glaciers, whispers of ancient storms. Water is the miracle that hides in plain sight. And in that sense, it isn't just life's foundation, it's life's most beautiful secret.